All right, this is the second of three lectures for the Module 5 compilation, Lexing and Parsing. We've been talking about parsing and how there's such a thing as top-down parsing, but the more common method is bottom-up parsing. Bottom-up parsing is where you start with the string, use the Backus-Naur form rules backwards, and then try to achieve the start symbol. And so here's an example of why you would do that. If you look at if you have a C and you want to go forward, you have three rules to choose from. But if you have a C, non-terminal C, and you want to go backwards, you only have one rule to choose from. So you can imagine with a larger grammar, like Java has about 170 rules, you really would like to go backwards more than forwards because it reduces the options that your compiler has, and it also reduces the possibility that you're going down the wrong part of a parse tree. You're taking a bad path and you'll have to retrace your steps. So in order to make this work out, though, let's introduce a new representation for strings. We had talked about, with Backus-Naur forms, doing derivations for strings. That's really amenable to the top-down form of parsing. If we're going to do bottom-up, let's introduce a new format. And this is a format that's graphical. And they're called parse trees. So what we talked about when we did derivations is you can have many derivations for a single string. That's common. But what the parse tree does, since it represents basically all of the steps of the derivation in one graphical image, it kind of takes sequence out of the picture. And if your BNF grammar is well formed, is well designed, you will have only one parse tree. So instead of having a bunch of different ways to derive the string, we only have one way to represent the string in a parse tree. A parse tree has all the terminals and non-terminals shown in the grammar that were used to derive the string. It is a tree form. Now, a graphical tree is a collection of nodes connected by edges, and every node is involved in a parent-child relationship. There are some special nodes. The root node has no parent, and there is only one root in the tree. And then the leaf nodes have no children. Those are the ones if you go furthest down. So if I go from the root and I start going down the tree and I come to the end of the line, that's a leaf. And again, because of the tree-like analogy, any single grouping of nodes would be called a branch. So, for a parse tree, the start symbol is the root. And from there, you start using the rules that were represented to develop the string. So we have the rule number 1, start symbol produces C. Rule number 2, a C can be replaced by an A, a C, and a B. Now notice, only one terminal or non-terminal is going to be in each node on the tree, only in each position on the tree. So if in the grammar C is replaced by ACB, that means that when you see a C, it's going to branch 3 times. It's going to be 3 separate items coming off of that C. So the C is replaced by ACB, and then we replace the next C with ACB, and then we use rule 3 to replace the last C with AB, and then all the A's can be replaced by an A, all the B's can be replaced by a B using rules 4 and 5. Now notice, if we did a derivation, we could have had a bunch of different derivations because we could have created all 6 of the non-terminals, capital AAA, capital BBB, and then taken a choice as to when we wanted to convert them to their terminals AAA, BBB. So there would be a lot of derivations. But the parse tree, there's only one. It kind of takes time out of the picture. So that's what a parse tree is. The root is the start node, and then you keep going down the paths using the non-terminals until finally you create the terminals at the leaves. And the sequence of this, the representation of this parse tree is a graphical representation of the derivation of AAABBB. And in fact, that single representation covers all possible derivations where we picked rules at different points in time. And the reason is, notice time is not shown here. It's just the end result. Another example, here's the language of palindromes. This was in your example practice problems previously. The language of palindromes with C indicating the center of the string. And here's our BNF grammar, except that I got a little help. There we go. There's our BNF grammar. And we want to do the string BAACAAB. So let's see, if I have the start symbol, I can only go to C, and then I have to figure out, okay, how do I create this BAACAAB? I can do that with a derivation, but I can also do it with the parse tree. Oh, okay, C goes to B, C, B. Notice, only one non-terminal at the end of each line, at the end of each connector here. C is the parent, B is the child, and then that B turns into the lowercase b, the terminal, that's the leaf. So C goes to BCB, C then goes to ACA, C then goes to, now I'm using rule, that would be rule 1, 2, 3, 4, terminal A, terminal C, terminal A, yeah, I know it's hard to tell the non-terminal C's from the terminal C's. Terminal A, terminal C, terminal A. So again, we could have many derivations for that string, but there's only one parse tree for that string. And you read the string from left to right on the leaves, BAACAAB. Here's another example. Again, this is from your practice problems in Module 2. This is the language of properly nested parentheses. And here's a grammar for it. It's pretty simple. And here's a string. And that string, again, has, I don't know if that has multiple derivations or not. But the parse tree would look like this. S goes to P, non-terminal P. P goes to non-terminal PP. That's how I'm going to get these side-by-side pairs of parentheses, right? P goes to non-terminal PP. And then I'm going to use rule, looks like rule 3. Non-terminal P goes to terminal left paren, non-terminal P, terminal right paren, and then rule 4, this P goes to terminal left paren, right paren, this P goes to terminal left paren, right paren, and there's your syntax, your parse tree or syntax tree. Now notice there's only one syntax tree per string. If we're not careful with our grammars, that will not be the case. Here, I've deliberately modified a grammar in order to make more than one parse tree for the same string. And if you have more than one parse tree for the string, it's called an ambiguous grammar. Now, I cannot stress this enough. The definition for an ambiguous grammar is that you can have more than one parse trees for at least one string in the language. In other words, if you had millions of strings in the language and only one of them had 2 or more parse trees, that's an ambiguous grammar. The only way you don't have an ambiguous grammar is if there is exactly one parse tree for every possible string in the language. Now, why is ambiguity even talked about? Well, because it's bad news for the parsers. If the parsers have a choice, for example, here's a choice. In this ambiguous grammar, if I see AB and I want to go backwards, should I go backwards to D? Or if I see AB, should I go backwards to C? It may be that if I take the wrong choice, I'm going to get a bad result. I may get an improper parse. So we need to always remember, computers are stupid, right? We never want to give them choices. So you always want to make sure that the parser has exactly one option going backwards. How do you know that that's going to be true? If you have exactly one parse tree. So here's 2 separate parse trees for the same string. That's bad. Okay, now again, you're going to be asked questions. I'm going to ask you, hey, here, create a grammar, create a parse tree. Tell me if your grammar is ambiguous, and you have to tell me why your grammar is not ambiguous. It's ambiguous because, look, I created 2 parse trees for this string. That's a proof that it's ambiguous. Or it is not ambiguous because I can make some kind of an argument that there will never be two parse trees for the language, for the grammar. Here's another example of ambiguous grammars. So I take that same nested parentheses and I did a cheap trick. I added a rule. I added a rule where instead of P going to PP, right, so up here P goes to PP, I added a rule that says P goes to PP and S also goes to PP. In other words, I just duplicated a rule. That's the easiest way to get an ambiguous grammar. When you get larger grammars, you may have ambiguity that's not that obvious. But the point is I can now make two parse trees, and that's a problem. Again, why is that a problem? Well, what if I see PP? If I want to use the rule backwards, should PP be replaced by P or should PP be replaced by S? One of them is right. One of them is wrong. So you may get an incorrect parse. Okay, so bottom-up parsers rely on this notion of a parse tree, and what they do is they, again, here's the string, right? Left paren, right paren, right paren, left paren, right paren. What they do is they start at these leaves and they start eating the string and they try to figure out where they can go up. So what we're going to do an example on the next video, and the idea is this. I say, okay, I've got a left-hand parentheses. Can I do anything with that? No. I've got another left-hand parentheses. Can I do anything with that? No. Now I've got a left and a right. Can I do anything with that? Oh yeah, I've got a rule for that. Left and right parentheses can go backwards to a P. So what they're going to do is collapse these two and replace it with P. Now what's happening is they're going up the tree. And now I see, okay, now I've got a left parentheses and a P. Can I do anything with that? No. I've got a left parentheses, P, right parentheses. Can I do anything with that? Wait a minute, I have a rule for that. Left paren, P, right paren, that gets replaced by P. Ah, so I can take these three things and go up the tree again. And what's happening is the compiler is taking in bits of strings, and when they get patterns that they can match to the rules, they go leftward on the BNF rule and replace that string with the non-terminal that generated that string. Okay, now I've got a P. Can I do anything with that? No. Okay, so I've got P, left paren. No, I can't do anything with that. P, left paren, right paren. Oh, I can do something with left paren, right paren, right? I use that rule to replace it with P, so I go up the string. Now I've got P, P. Can I do anything with that? Pretend this is not an ambiguous grammar. P, P gets replaced by P. That goes there. P gets replaced by S. I'm out of string. I'm at my start symbol. It's basically an empty stack acceptance criteria. I'm out of string. I'm at my start symbol, and I would accept the string. So we're going to go into detail about that in the next lecture.